So what we're going to look at here, this is one of the most valuable tools in algebra. And people come back to this all the time, and that's just our order of operations tree, right? We saw order, let's get rid of earbuds and phones and all that stuff, please, and click and close. So we looked at this last unit, right? You just finished up the test on this where we talked about order of operations. The PEMDAS tree does more than just simplify though, right? What we were doing in unit 1 was just the blue arrow. We were starting with some kind of numerical expression and simplifying it down to a single number, or perhaps we were evaluating and then simplifying, right? Plugging in values of a variable and then simplifying using these steps. And well, that's something you'll continue to use forever in algebra. But we're going to add another direction to this. We're going to start to look at equations now. We didn't look at any equations last time, right? We were just really focusing on kind of background information, the sets of numbers, the properties of real numbers, how to do some practice converting like word expressions into math expressions, but we didn't solve anything. Okay, now we're going to start to solve equations, and we're going to start with linear equations. We're going to continue to kind of ease into things a little bit before we jump into uh, higher level equations, quadratic equations, and polynomial equations and things. We're going to focus on linear equations because there's still some stuff that you guys probably haven't done that we need to address, even with linear equations. So first of all, what is a linear equation? Well, linear equation is just an equation where there's only one variable, and that variable is to the first power. That's it. That's a linear equation, okay? So typically it's going to involve, for us, typically it's x. This doesn't have to be. It could be any variable, but usually it would be an x, and that x is never being squared. It's never being square rooted. It's just always to the first power. So when we're solving a linear equation, this is equivalent to isolating the variable on one side of the equation. And that's probably no surprise to you, right? You've done a lot of that stuff. But I want you to think about those two things in the same way. So if solving a linear equation is equivalent to isolating the variable, well, then we can use PEMDAS, we can use our order of operations tree to tell us what steps to do in what order. All we have to do is just invert the direction of the arrow. And instead of using regular order of operations, we're going to use what's called inverse operations. And I think I'll even write that down. So this stuff over here, a lot of times we refer to this as inverse operations. Those are the operations we use to solve equations. Okay, so then when we're solving more complex linear equations, sometimes we have to do a little bit of both. And here's how you can think about this. There's a flow to the direction of the PEMDAS tree that addresses any linear equation. If things start off looking somewhat complicated, like you've got lots of x terms and you've got lots of things spread on both sides of the equation, we're always going to start off by simplifying. And here's the rule. We're going to follow regular order of operations, top-down PEMDAS, until we can point to a single instance of the variable. So if x is our variable, I should be able to point to a single x in the equation. As soon as I can do that, then I can flip things around and use inverse operations and go the opposite direction on the order of operations tree to isolate the variable. Okay? So have you guys talked about it in this way before? So you've talked about using the order of operations tree going down and up for solving. Give me a 1 to 5 on that. I just want to, what's your level of familiarity with that? Okay, we're all over the board. That's fine. No big deal. Doesn't matter if you've seen it or not, honestly. Okay, so let's start simple. We're going to solve this equation for x. You guys can all, this is no big deal. You can all do this. Easy to do. Okay, so first of all, we ask ourselves, can we point to a single variable? We can, right? We can point to a single variable. If I can point to a single variable, which is right there, then I can start by using inverse operations, right? I'm just going to use the operations necessary to isolate that variable. They're so trivial here that you guys probably just don't even think about it in this way. But here's the thing. Later on, we're going to use this same approach for more difficult problems. And so I really do want to focus on what those steps are, because very soon, within a month, we'll be doing this with certain types of quadratic equations. where all of a sudden now those steps aren't quite as obvious, right? Okay, so what's the first thing we would do then if we're isolating the variable? Well, moving from top or from bottom to top, first we have to add or subtract. Okay, so what's our first step going to be? Add 3. Okay, now let's look at that. We're going to add 3. Addition and subtraction go together, right? Addition undoes subtraction, and subtraction undoes addition, right? Same thing for multiplication and division. They go together and they undo each other. So I'm going to undo this subtraction by adding, right? So there's our first step. I mean, I'm going through this very basic level. I know you're probably thinking, okay, we got this. So step 1 is we're going to add 3 to both sides. So the 3's cancel. Then I get 2x equals 15. What's my next step? Divide. I've got multiplication there, right? That x is being multiplied. So I'm going to use its companion, division, to undo the multiplication, right? Those are inverse processes. Inverse is an important word in math. We'll come back to that in the future too, in different circumstances, and it has slightly different meanings, but very, very similar. So next step is we're going to divide by 2, and we got it. We isolated the variable, and we ended up getting x equals 15 halves. How do we want to write that? Do I want to put that as a mixed number? No. That's fine. That's a great answer. 15 halves, 15 over 2, is good. We want to leave it in fractional form. That is an improper fraction because the numerator is bigger than the denominator, but that's all right. We don't care. We don't care. Question. Oh, yeah, that's fine. Yep, go for it. Yep. Okay, so next question for you is, how would you, whenever you're solving an equation, here's one thing that's really nice about solving equations. When it comes time for the test and you've got to input your answers and hit submit, once you do that, you're committed, right? But before you push submit, you can always tell if you have the right answer or not. How? Plug it in, right? What does it mean to solve an equation? To solve an equation for x in this case means that we are going to find all of the values of x that satisfy the equation. That's really what that's asking us to do. Anytime we solve something, and I'm going to write that down so it's in the notes. In this case, there's only one, but in the future, there may be more. What does it mean to satisfy the equation? Make it true, right? Make it a valid equation. They make it work. So all I would have to do when I get an answer is plug it back into my original equation and see if it works. Okay, that's normally pretty easy to do. A lot of times you can just even do it in your head. What makes this one a little bit tougher? Say it again. It's a fraction. Okay, so plugging that fraction in might make things a little bit tougher. It's not too bad because if I'm multiplying 15 halves times 2, it's going to cancel the denominator. What's 15 halves times 2? 15. 15 minus 3 is 12. It works. Okay, but what if it were more complicated? What if it were an equation that involved lots of terms? Eventually, it might involve powers, it might involve roots, it might involve all kinds of ugly things that make it more difficult to check something numerically by just plugging it in and thinking about what the answer should be, right? It might take a lot of work, just arithmetic work, to see if it actually does satisfy the equation. I want to show you a trick using Desmos, which is fine. I mean, we're getting to a point in math where arithmetic is not the focus of the class, right? The focus of the class is algebra and using algebra to build models and doing interesting things with algebra. And so we want to use the available technology to maybe do some arithmetic for us, to cut down our time. We don't want to waste time doing that when we could be focusing on other things. Later in math, like you go far enough in math in college, and even things like solving big calculus problems like differential equations. A lot of times people will even use computer algebra systems to do that. At that point, that might even be considered kind of low level stuff. They'll even just use computer algebra systems to solve that low level stuff so they can be working on really high level stuff like topological math or things that are, really very theoretical. So this is fine for us to use technology, and here's how you can. You'll always have access on a test to at least Desmos Scientific. So let's just use Desmos Scientific to check this solution. Okay, here's how you can do it. We are going to, all we have to do here, and in this case, it's the right side is pretty trivial. It's already 12. Okay, but in some cases, I'll have variables maybe on both sides initially. So I'm just going to set up a function, and we haven't talked about function notation yet, but this is, did I show you something kind of like this at all? I did a little bit, right? Where we evaluated a function. Okay, good. We're gonna do the same thing here again. So f of x equals, the left side is 2x minus 3. Okay, now if I had variables on the right side, I would set it equal to g of x. And I'm just gonna plug in the values that are the solutions. So there's the function that's gonna give me the value of what's on the left side of the equal sign. If I plug in my answer of 15 halves, f of 15 halves, look what it tells me. The answer is 12. That's what I have on the right side, so it checks, doesn't it? Everybody see that? Okay. So let me just take a picture of that for our notes. Okay, so we can just put a big check there and call her good. Questions? Does that all make sense? Okay. Next step. So what happens if we get a little more complicated and we've got a bunch of variables on both sides? Now, you guys intuitively know what to do, right? What would you do? Say it again. Distribute. Okay, good. Distributive property, and then we'll collect all the what's next then? I distribute, combine like terms. Going to push the variables to one side, right? Collect them all on one side. Okay, so this is really just at this point. Can I point to a single variable? I can't, right? So that means I've got to simplify, right? I've got to work down the left side of this equation. So, and you know this intuitively what to do. There's nothing in parentheses that I can simplify. There are parentheses here, but if I look inside those parentheses, I can't do anything. I can't combine those terms because they're not like terms. Again, over here, I've got parentheses, but inside the parentheses, there's nothing to be simplified. Agreed? So we work our way down. Exponents, no exponents, multiplication, yes. What's the multiplication here? Distributing, exactly. Okay, so we distribute the -3, we distribute the -2, and what's that going to give me? Good, plus 30 minus y equals plus 10. Okay, so on the left side, what would our next step probably be? Combine the y's, good. So we get -19y plus 30 equals -2y plus 10. Okay, so now here's another weird thing I'm going to say. You kind of want to think about algebra almost like a video game, right? You want to think about it conceptually as pushing things around in the equation from left to right. Where do we want to push the variables here? Because ultimately our goal is to isolate the variables on one side. We want to stick them on the right or the left? The left, I would, so over here? Okay, if I stick them over here, it's going to work. Absolutely, it's going to work. That would mean adding 2y to both sides. Can anybody tell me? I'm actually going to suggest it might be better to push the y's to the right this time. How come? Good. We'd rather have a positive coefficient. With linear equations, it's not that big a deal. But again, later on when we get into heavier weight equations, that becomes more useful, that concept, right? We'd rather be dividing by positives than negatives. okay? Does it matter which side the y is on? No, it doesn't. We just have to isolate it on a side of the equation. There's no preference, okay? So we'll go ahead and push the y's to this side. In the future, all I'll do to indicate that is just maybe make an arrow that looks like that, right? That's our work. We're just going to push the 19y over to that other side by adding it. For now, let's show that step. Now let's think ahead just a little bit while we're at this. That's going to push the y's to the right. My goal is to isolate the y, so why not combine some steps here? If I want to push the variables to the right, where do I want to push the constants, the numbers? To the left, right? Because I want to ultimately just isolate that variable. So then we'll subtract 10 from both sides at the same time. So we're canceling those guys and we're canceling those guys, right? And then what do we have? Now we've got 20 equals what, 17y. Finally, I can point to a single variable. What's the only step I need to isolate the variable? Divide. Yeah, good. So if I divide by 17, I get y equals 20/17, right? And we can check ourselves. How'd we do? Looks like we got it. Okay, give me thumbs. How are we on this? Okay. Okay. Okay, let's look at a couple special cases here. So same kind of thing here. You guys would tell me, what would I do first? Distribute. Okay, so if I distribute the 2 and I distribute the 4, that's going to give me what? 2x minus 16 plus 2x equals 4x plus 24 minus 40. Combine like terms on both sides, okay? So I get, let's see, 4x minus 16 equals 4x minus 16, okay? Next step would logically be to push the variables to one side normally, right? Okay, well, what happens if I subtract 4x from both sides? They go away, don't they? Okay, and that's important. We actually do want to push the variables. If I push these 4x's to that side, they're just going to cancel, aren't they? So we are going to subtract 4x from both sides. And if we do that, look what happens. We get the answer negative 16 equals negative 16. The variables disappeared when we solved this equation, and we got a statement that's true or false. True. How do we interpret that? Remember, how do we, anybody tell me what's going on there? How many solutions would there be? Okay, what are those infinite solutions? All real numbers, right? What that's telling us is that any value of x I plug in is going to satisfy this equation, right? Because the x has disappeared. That's the way the math gods tell us that this equation is if something goes away in the algebra, it tells us that the equation is insensitive to that thing. So in this case, it's insensitive to the value of x, meaning it doesn't matter. That you change the value of x, it's not going to affect the outcome at all, okay? So what would our choice be then? If we go down, this is the way the question will look on your homework. We've got to select the correct row. Well, which one's it going to be? It's going to be B, isn't it? Yeah. Okay, that's it. Okay, there is no x value, all real numbers. There's no specific x value. Okay, how about one like this guy? Same kind of thing, right? What if I distribute this time? I get 2x plus 10 plus 2 equals 2x plus 7. So 2x plus 12 equals 2x plus 7. Next step. Say it again. Subtract 2x. Okay. And again, the variables cancel, but this time I'm left with a false statement, 12 equals 7. Well, that's not true. So how do we interpret that? If we solve a linear equation, the variables fall away, and I am left with a false statement. No solution. Okay, good. So you're remembering all this. So then this one is that guy. There's no solution. Okay, and here's just a quick reminder for the notes, some additional, maybe some terminology we can apply to this. If an equation in one variable, right, has no solution, we only have one variables in these equations, it's been x in every case. This is called a contradiction, and it means that there are no solutions, right? If all the variables fall away and you get a false statement like this, for example, in this example, then you know there's no solution, it's a contradiction. If first instance we looked at, the variables fell away and we had a true statement, that means there's infinitely many solutions, all real numbers, then we call this an identity. Okay, that in math, an identity is something that is always true. Okay. Okay, so when are we out of here? Remind me. Okay, so we got a little bit of time. Okay, so let's look at one more thing then maybe for today. Have you guys done this? Have you spent some time clearing fractions? Okay, let's review it anyway, because there's one layer to this I bet you haven't done. So clearing fractions, it's very, very useful whenever you've got an equation that involves a sum of terms on both sides of the equation and you see one or more fractions, right? We could solve this using traditional, you could, right? Fractions are just numbers. I could use the same steps that we used in the last few examples and it would work. But the disadvantage is I'm doing all this arithmetic with fractions, which is very cumbersome, right? So our strategy instead then is going to be, let's do a little bit of work up front and let's trade this complicated looking linear equation with all these darn fractions for a much easier one that has the same solutions where we'll eliminate the fractions. Okay, what is our strategy here for eliminating the fractions? Do you remember? Say it again. Okay, of which side? Or both sides? Both sides, yeah. So we want to find the least common denominator of all the denominators on both sides of the equation, and we're going to multiply through by that, okay? So what would that be here? I'm hearing 20, I'm hearing 40. Which one is it? I'm still hearing two things, 20 or 40? Okay, it is 40, isn't it, right? How do you know? We talked a little bit about this before. Just quick review of the stuff we talked about before with this. How do we find the LCD? It's the least common multiple of all denominators. So we're going to make a list of multiples of which one and check them. The biggest one, right? The biggest one is 20. So we'll just make a list of the multiples of 20, which are 20, 40, 60, 80, etc. And we'll just go walk through that list until we find one that's divisible by all the other denominators, okay? Well, 20 doesn't work, does it? 8 doesn't go into 20, so we can cross that one out, but 40 does work. 8, 5, and 4 all divide evenly into 40, so that we know that's our answer. Okay, that's our LCD. Now, what do we do with that 40? Okay, so we could get common denominators, but we don't need to. That's a lot of extra work. It would work. But what can we do instead? Now we've got an equation here. I'm not going to spend a lot of time with you guys talking about properties of equality and all, because this is so intuitive. Essentially, what does it mean when I have an equation? What is that equal side telling me that I have to do on both sides of the equation? The same thing, right? I have to treat both sides equally, okay? So what am I going to do to both sides of the equation here to cancel all of those denominators? I really don't need I found what the common denominator would be, but I don't really need to add up fractions using a common denominator. Because I've got an equation here, would everybody agree I could add 5 to both sides of this and it would stay a true statement? Agreed? Still an equation. I could divide both sides by 3 and it would stay equals. Both left and right would still be equals. I could multiply both sides by the same thing, and I'm still treating both sides of the equation equally, and so it remains an equation, right? What am I going to do here? So maybe you guys haven't done as much with this as I thought you had. What could I do here to clear the fractions? Oh, this is new territory, huh? Okay, so we are going to multiply both sides by the LCD, okay? The least common denominator, right? Now, there's a way to show this that is kind of convenient. You could just say, I'm going to put brackets around the whole equation, and I'm going to put a 20 or a 40 out front, and then I'll just distribute that all the way through. That means I'm multiplying each side by 40, right? Because each side just consists of terms that are being added or subtracted. I'm really just distributing the 40 to both sides, aren't I? Give me thumbs. We good with that? Okay, so if I distribute the 40, the advantage of that is you can maybe start to see this. All the denominators are going to cancel then, aren't they? Right? Because 40 is a number that we handpicked because all of the denominators divide evenly into it, right? So let's think about what this looks like when we distribute. I'm going to show this to you the long way first, and then we'll look at a shortcut, a really good shortcut that I'll give you. If I distribute 40, what's really in the denominator of 40? 1. Okay. So if I multiply 40 over 1 times each of these, what's that give me? Well, 40 times 5 is 200 over 8 times x. 40 times 3 is 120. Again, I get 120 there, don't I? 120 over 4x. And then finally, 40 times 17 is going to be 680. And so I get some pretty big numbers, right? I could reduce those fractions, and I'm going to get answers that are non-fractional, okay? 200 over 8, can you guys tell me what that is? 25, good. So I get 25x. 120 over 5 is, I heard it, I think I heard it. Someone say 24? Yeah, good. Minus 24 equals, well, there's a 120 over 4, 30, okay. And then 680 over 20, 34, good. And now it's easy, isn't it? Right? Now look, we've got a very simple linear equation where I don't have fractions, and you guys could all solve that in a matter of just, seconds probably, right? Okay, but that was kind of cumbersome, wasn't it? Getting those great big numbers. Show you a great trick. Here's what you can always do whenever you are clearing fractions like this, and you've just got a bunch of things added or subtracted on both sides. Awesome trick. You know that the denominators are all going to divide evenly into the least common denominator. You got two operations to do. You've got to multiply and then divide, right? But nobody says you have to multiply first. Let's be smarter about this, and let's divide first and then multiply by whatever you end up getting when you reduce, okay? So 40 over 8 is equal to what? 5. Look at this. So then I'm going to cancel the denominator, and that's what gets multiplied by the numerator. How easy is that, right? Way easier. You can do it in your head very easily. So then we end up with our first term being 5 times 5 is 25x. 40 over 5 is 8 times 3, 24. So I get minus 24. 40 over 4, 10 times 3, 30x. 40 over 20, 2 times 17. How much easier is that, right? Way easier. Okay, so when you're clearing fractions, reduce first and then multiply by the numerator. Way easier, okay? And then from here, we just got a minute or two, which is all we need. Where am I going to push the x's, right or left? To the right, good. Okay, so we'll subtract 25x. That's supposed to be a 5, yikes. And then, so that means if the x's are going right, where are the numbers going? Left, okay, so we'll subtract 34. That gives us what? So negative 58 equals 5x. Last step, divide by 5, and we get x equals negative 58 fifths. Good? All right, call her a day.